Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Zunur bin Muhammad Anor. My final year project title is Performance Evaluation of Asymmetric DC Source Reduced Switch Multi-Level Inverter Topologies for using voltage stress and switching characteristic. The objective of this project is to analyze and compare several level inverter topologies using asymmetric DC source. I focus on evaluating voltage stress across switches, harmonic distortion in the output waveform, and overall inverter efficiency. This study is fully simulation-based. I use PitSim software to model each topology, construct switching control, and measure result. The tool enables me to build realistic inverter circuits and conduct detailed performance evaluation efficiently. The main tool I use in this project is PitSim, which stands for Power Simulation Software. It is highly suitable for power electronic application because it offers powerful and specialized features for designing and testing inverter circuit. PitSim allows me to model RSMLI topologies with full control over DC source value, switching signal, and load condition. One of the key reasons I select PitSim was its built-in FFT analysis, which helped me to measure total harmonic distortion (THD) and assess the waveform quality of each topology. Okay, now I will demonstrate how the tool was used to simulate and analyze the inverter topologies. First, here is the 7-level reduced multi-level inverter circuit that I built in PitSim. I use two asymmetric DC source, which is 48 volt and 96 volt, connected across 6 MOSFET switches, and a relative load was 50 ohm. To control the switches, I use the half-height HH modulation method, which helped reduce the number of switching transitions while maintaining waveform quality. I manually define a switching angle in the control logic blocks. The angle used for waveform synthesis were A1 equal to 9.59 degrees, A2 30 degrees, and A3 56.44 degrees. These angles are crucial because they determine exactly when each switch should turn on or turn off to create the desired step level. Once the setup was complete, I ran the simulation. As shown here, the output waveform generated is a clean 7-level step voltage pattern, which confirmed that the control logic and circuit configuration were correct. Then I used the FFT analysis tool in PitSim to evaluate waveform quality. I performed the FFT directly on the output voltage waveform. The frequency spectrum clearly showed the harmonic component, and the total harmonic distortion for this configuration was approximately 11%. To better visualize the harmonic content, we generate the graph using Excel by copying the FFT result data from PitSim. Okay, now this is the gating signal setup. The first, I place a voltage probe on each switch to observe the gating signal. We generate each gating signal to see the exact timing of when each switch turn on and off. This allows me to verify that the switching logic and defined angles were correctly implemented to produce the intended output waveform. Okay, now let's go to the voltage stress setup. For voltage stress analysis, I insert a value of 1 into each voltage flag connected to the switch. This allows me to monitor the voltage drop across each switch. We then record this value and use Excel to generate a voltage stress graph. It helps visualize how much voltage each switch handles during operation and assess the reliability of the design. Tool limitation become a concern in this project. PitSim use ideal component, so it cannot simulate thermal effect or parasitic losses. It also lacks real-time control features, require manual switching input, and offer limited graph customization compared to MATLAB. In conclusion, PitSim support the simulation and performance analysis of multiple 7-level reduced multi-level inverter topologies. It enables accurate waveform generation, voltage stress monitoring, and THD measurement, while also allowing for quick design and testing. Through the project, I learned that PitSim is fast and accurate, for power circuit modeling. However, it is limited by its ideal-based simulation and lack of thermal or embedded system modeling. Overall, this project depends my understanding of inverter behavior and the practical value of simulation before hardware implementation.